For the law governing blackbody radiation, see Planck's law. The Planck constant is a physical constant that is the quantum of action in quantum mechanics. Published in 1900, it originally described the proportionality constant between the energy of a charged atomic oscillator and the wall of a black body, and the frequency of its associated electromagnetic wave. Its relevance is now integral to the field of quantum mechanics, describing the relationship between energy and frequency, sometimes known as the Planck-Einstein relation. In 1905 the energy of a charged atomic oscillator, was theoretically associated with the energy of the electromagnetic wave itself, representing the minimum amount of energy required to form an electromagnetic field. Further investigation of quanta revealed behavior associated with an independent unit as opposed to an electromagnetic wave and was eventually given the term photon. The Planck-Einstein relation now describes the energy of each photon in terms of the photon's frequency. This energy is extremely small in terms of ordinary experience. Since the frequency, wavelength I, and speed of light c are related by I1/2 equals c, the Planck-Einstein relation for a photon can also be expressed as. The above equation leads to another relationship involving the Planck constant. Given p for the linear momentum of a particle, the de Broglie wavelength I of the particle is given by. In applications where it is natural to use the angular frequency, it is often useful to absorb a factor of 2I into the Planck constant. The resulting constant is called the reduced Planck constant or Dirac constant. It is equal to the Planck constant divided by 2I, and is denoted as section. The energy of a photon with angular frequency I per mil, where I per mil equals A2I I1/2, is given by. The reduced Planck constant is the quantum of angular momentum in quantum mechanics. The Planck constant is named after Max Planck, the founder of quantum theory, who discovered it in 1900, and who coined the term quantum. Classical statistical mechanics requires the existence of H. Planck discovered that physical action could not take on any indiscriminate value. Instead, the action must be some multiple of a very small quantity. This inherent granularity is counterintuitive in the everyday world, where it is possible to make things a little bit hotter, or move things a little bit faster. This is because the quanta of action are very, very small in comparison to everyday macroscopic human experience. Hence, the granularity of nature appears smooth to us. Thus, on the macroscopic scale, quantum mechanics and classical physics converge at the classical limit. Nevertheless, it is impossible, as Planck discovered, to explain some phenomena without accepting the fact that action is quantized. In many cases, such as for monochromatic light or for atoms, this quantum of action also implies that only certain energy levels are allowed, and values in between are forbidden. In 1923, Louis de Broglie generalized the Planck-Einstein relation by postulating that the Planck constant represents the proportionality between the momentum and the quantum wavelength of not just the photon, but the quantum wavelength of any particle. This was confirmed by experiments soon afterwards. Value. The Planck constant has dimensions of physical action. These are the same as those of angular momentum, that is, energy multiplied by time, or momentum multiplied by distance. In SI units, the Planck constant is expressed in joule-seconds or. The value of the Planck constant is. The value of the reduced Planck constant is. The two digits inside the parentheses denote the standard uncertainty in the last two digits of the value. The figures cited here are the 2010 CODATA recommended values for the constants and their uncertainties. The 2010 CODATA results were made available in June 2011 and represent the best-known, internationally accepted values for these constants, based on all data available as of 2010. New CODATA figures are scheduled to be published approximately every 4 years. Significance of the value: the Planck constant is related to the quantization of light and matter. Therefore, the Planck constant can be seen as a subatomic scale constant. In a unit system adapted to subatomic scales, the electron volt is the appropriate unit of energy and the petahertz the appropriate unit of frequency. Atomic unit systems are based on the Planck constant. The numerical value of the Planck constant depends entirely on the system of units used to measure it. When it is expressed in SI units, it is one of the smallest constants used in physics. This reflects the fact that on a scale adapted to humans, where energies are typically of the order of kilojoules and times are typically of the order of seconds or minutes, Planck constant is very small. Equivalently, the smallness of Planck constant reflects the fact that everyday objects and systems are made of a large number of particles. For example, green light with a wavelength of 555 nanometers has a frequency of 540 ATHz. Each photon has an energy E of high 1/2 equals 3.58 A, 10 in 19 a J. That is a very small amount of energy in terms of everyday experience, but everyday experience is not concerned with individual photons any more than with individual atoms or molecules. An amount of light compatible with everyday experience is the energy of 1 mole of photons. Its energy can be calculated by multiplying the photon energy by the Avogadro Constant, nor per mole 6.022 A, 1023 a molar 1. The result is that green light of wavelength 555 nm has an energy of 216 kJ per mole, a typical energy of everyday life. Origins: Blackbody radiation. In the last years of the 19th century, Planck was investigating the problem of blackbody radiation first posed by Kirchhoff some 40 years earlier. It is well known that hot objects glow, and that hotter objects glow brighter than cooler ones. The reason is that the electromagnetic field obeys laws of motion just like a mass on a spring, and can come to thermal equilibrium with hot atoms. When a hot object is in equilibrium with light, the amount of light it absorbs is equal to the amount of light it emits. If the object is black, meaning it absorbs all the light that hits it, then it emits the maximum amount of thermal light too. The assumption that blackbody radiation is thermal leads to an accurate prediction. The total amount of emitted energy goes up with the temperature according to a definite rule, the Stefani-Boltzmann law. But it was also known that the color of the light given off by a hot object changes with the temperature, so that white hot is hotter than red hot. Nevertheless, Wilhelm Wien discovered the mathematical relationship between the peaks of the curves at different temperatures, by using the principle of adiabatic invariance. At each different temperature, the curve is moved over by Wien's displacement law. Wien also proposed an approximation for the spectrum of the object, which was correct at high frequencies but not at low frequencies. It still was not clear why the spectrum of a hot object had the form that it has. Planck hypothesized that the equations of motion for light are a set of harmonic oscillators, one for each possible frequency. He examined how the entropy of the oscillators varied with the temperature of the body, trying to match Wien's law, and was able to derive an approximate mathematical function for blackbody spectrum. However, Planck soon realized that his solution was not unique. There were several different solutions, each of which gave a different value for the entropy of the oscillators. To save his theory, Planck had to resort to using the then controversial theory of statistical mechanics, which he described as an act of despair. I was ready to sacrifice any of my previous convictions about physics. One of his new boundary conditions was to interpret UN, the vibrational energy of n oscillators, not as a continuous, infinitely divisible quantity, but as a discrete quantity composed of an integral number of finite equal parts. Let us call each such part the energy element I micron. With this new condition, Planck had imposed the quantization of the energy of the oscillators, a purely formal assumption. Actually I did not think much about it in his own words, but one which would revolutionize physics. Applying this new approach to Wien's displacement law showed that the energy element must be proportional to the frequency of the oscillator, the first version of what is now sometimes termed the Planck-Einstein relation. Planck was able to calculate the value of H from experimental data on blackbody radiation. His result, 6.55 a, 10 a 34 Gs, is within 1.2% of the currently accepted value. He was also able to make the first determination of the Boltzmann constant Kb from the same data and theory. Prior to Planck's work, it had been assumed that the energy of a body could take on any value whatsoever, that it was a continuous variable. The Rayleigh-Eurodgenes law makes close predictions for a narrow range of values at one limit of temperatures, but the results diverge more and more strongly as temperatures increase. To make Planck's law, which correctly predicts blackbody emissions, it was necessary to multiply the classical expression by a complex factor that involves h in both the numerator and the denominator. The influence of h in this complex factor would not disappear if it were set to 0 or to any other value. Making an equation out of Planck's law that would reproduce the Rayleigh-Jeans law could not be done by changing the values of h, of the Boltzmann constant, or of any other constant or variable in the equation. In this case, the picture given by classical physics is not duplicated by a range of results in the quantum picture. The Blackbody problem was revisited in 1905, when Rayleigh-Jeans and Einstein independently proved that classical electromagnetism could never account for the observed spectrum. These proofs are commonly known as the Ultraviolet Catastrophe, a name coined by Paul Ehrenfest in 1911. They contributed greatly to convincing physicists that Planck's postulate of quantized energy levels was more than a mere mathematical formalism. The very first Solvay conference in 1911 was devoted to the theory of radiation and quanta. Max Planck received the 1918 Nobel Prize in Physics in recognition of the services he rendered to the advancement of physics by his discovery of energy quanta. Photoelectric effect. The photoelectric effect is the emission of electrons from a surface when light is shone on it. It was first observed by Alexander Edmund Becquerel in 1839, although credit is usually reserved for Heinrich Hertz, who published the first thorough investigation in 1887. Another particularly thorough investigation was published by Philip Léonard in 1902. Einstein's 1905 paper discussing the effect in terms of light quanta would earn him the Nobel Prize in 1921, when his predictions had been confirmed by the experimental work of Robert Andrews Millikan. The Nobel Committee awarded the prize for his work on the photoelectric effect, rather than relativity, both because of a bias against purely theoretical physics not grounded in discovery or experiment, and dissent amongst its members as to the actual proof that relativity was real. Prior to Einstein's paper, electromagnetic radiation such as visible light was considered to behave as a wave, hence the use of the terms frequency and wavelength to characterize different types of radiation. The energy transferred by a wave in a given time is called its intensity. The light from a theater spotlight is more intense than the light from a domestic light bulb. That is to say that the spotlight gives out more energy per unit time than the ordinary bulb, even though the color of the light might be very similar. Other waves, such as sound or the waves crashing against a seafront, also have their own intensity. However, the energy account of the photoelectric effect didn't seem to agree with the wave description of light. The photoelectrons emitted as a result of the photoelectric effect have a certain kinetic energy, which can be measured. This kinetic energy is independent of the intensity of the light, but depends linearly on the frequency. And if the frequency is too low, no photoelectrons are emitted at all, unless a plurality of photons, whose energetic sum is greater than the energy of the photoelectrons, acts virtually simultaneously, assuming the frequency is high enough to cause the photoelectric effect. A rise in intensity of the light source causes more photoelectrons to be emitted with the same kinetic energy, rather than the same number of photoelectrons to be emitted with higher kinetic energy. Einstein's explanation for these observations was that light itself is quantized. That the energy of light is not transferred continuously as in a classical wave, but only in small packets, or quanta. The size of these packets of energy, which would later be named photons, was to be the same as Planck's energy element, giving the modern version of the Planck-Einstein relation. Einstein's postulate was later proven experimentally. The constant of proportionality between the frequency of incident light and the kinetic energy of photoelectrons was shown to be equal to the Planck constant. Atomic structure. Niels Bohr introduced the first quantized model of the atom in 1913, in an attempt to overcome a major shortcoming of Rutherford's classical model. In classical electrodynamics, a charge moving in a circle should radiate electromagnetic radiation. If that charge were to be an electron orbiting a nucleus, the radiation would cause it to lose energy and spiral down into the nucleus. Bohr solved this paradox with explicit reference to Planck's work. An electron in a Bohr atom could only have certain defined energies n, where co is the speed of light in vacuum, Ra is an experimentally determined constant and n is any integer. Once the electron reached the lowest energy level, it could not get any closer to the nucleus. This approach also allowed Bohr to account for the Rydberg formula, an empirical description of the atomic spectrum of hydrogen, and to account for the value of the Rydberg constant Ra in terms of other fundamental constants. Bohr also introduced the quantity h/2i euro, now known as the reduced Planck constant, as the quantum of angular momentum. At first, Bohr thought that this was the angular momentum of each electron in an atom. This proved incorrect and, despite developments by Sommerfeld and others, an accurate description of the electron angular momentum proved beyond the Bohr model. The correct quantization rules for electrons are euro in which the energy reduces to the Bohr model equation. In the case of the hydrogen atom, a euro were given by Heisenberg's matrix mechanics in 1925 and the Schrödinger wave equation in 1926. The reduced Planck constant remains the fundamental quantum of angular momentum. In modern terms, if J is the total angular momentum of a system with rotational invariance, and Jz the angular momentum measured along any given direction, these quantities can only take on the values. Uncertainty principle. The Planck constant also occurs in statements of Werner Heisenberg's uncertainty principle. Given a large number of particles prepared in the same state, the uncertainty in their position, Ix, and the uncertainty in their momentum, Ip, obey. Where the uncertainty is given as the standard deviation of the measured value from its expected value. There are a number of other such pairs of physically measurable values which obey a similar rule. One example is time versus energy. The either-or nature of uncertainty forces measurement attempts to choose between trade-offs, and given that they are quanta, the trade-offs often take the form of either-or, rather than the compromises and gray areas of time series analysis. In addition to some assumptions underlying the interpretation of certain values in the quantum mechanical formulation, one of the fundamental cornerstones to the entire theory lies in the commutator relationship between the position operator and the momentum operator, where IH is the Kronecker delta. Dependent physical constants. The following list is based on the 2006 CODATA evaluation. For the constants listed below, more than 90% of the uncertainty is due to the uncertainty in the value of the Planck constant, as indicated by the square of the correlation coefficient. The Planck constant is the fundamental physical constant which is known to the lowest level of precision, with a relative uncertainty error of 5.0 10^8. Rest mass of the electron. The normal textbook derivation of the Rydberg constant Ra defines it in terms of the electron mass μ and a variety of other physical constants. However, the Rydberg constant can be determined very accurately from the atomic spectrum of hydrogen, whereas there is no direct method to measure the mass of a stationary electron in SI units. Hence the equation for the calculation of μ becomes, where co is the speed of light and I plus or minus is the fine structure constant. The speed of light has an exactly defined value in SI units, and the fine structure constant can be determined more accurately than the Planck constant. The uncertainty in the value of the electron rest mass is due entirely to the uncertainty in the value of the Planck constant. Avogadro constant. The Avogadro constant Na is determined as the ratio of the mass of 1 mole of electrons to the mass of a single electron. The mass of 1 mole of electrons is the relative atomic mass of an electron R, E, which can be measured in a pinning trap, multiplied by the molar mass constant μ, which is defined as 0.001 kg per mole. The dependence of the Avogadro constant on the Planck constant also holds for the physical constants which are related to amount of substance, such as the atomic mass constant. The uncertainty in the value of the Planck constant limits the knowledge of the masses of atoms and subatomic particles when expressed in SI units. It is possible to measure the masses more precisely in atomic mass units, but not to convert them more precisely into kilograms. Elementary charge. Sommerfeld originally defined the fine structure constant I plus or minus as where E is the elementary charge, I micron 0 is the electric constant, and I 1/4 0 is the magnetic constant. The latter two constants have fixed values in the International System of Units. However, I plus or minus can also be determined experimentally, notably by measuring the electron spin G factor Ge, then comparing the result with the value predicted by quantum electrodynamics. At present, the most precise value for the elementary charge is obtained by rearranging the definition of I plus or minus to obtain the following definition of E in terms of I plus or minus and H. Bohr mountain and nuclear mountain. The Bohr mountain and the nuclear mountain are units which are used to describe the magnetic properties of the electron and atomic nuclei respectively. The Bohr mountain is the magnetic moment which would be expected for an electron if it behaved as a spinning charge according to classical electrodynamics. It is defined in terms of the reduced Planck constant, the elementary charge and the electron mass, all of which depend on the Planck constant. The final dependence on Ha1/2 can be found by expanding the variables. The nuclear mountain has a similar definition, but corrected for the fact that the proton is much more massive than the electron. The ratio of the electron relative atomic mass to the proton relative atomic mass can be determined experimentally to a high level of precision. Determination. In principle, the Planck constant could be determined by examining the spectrum of a black-body radiator or the kinetic energy of photoelectrons, and this is how its value was first calculated in the early 20th century. In practice, these are no longer the most accurate methods. The CODATA value quoted here is based on 3-watt balance measurements of Kj2OK and one interlaboratory determination of the molar volume of silicon, but is mostly determined by a 2007-watt balance measurement made at the U.S. National Institute of Standards and Technology. 5 other measurements by 3 different methods were initially considered, but not included in the final refinement as they were too imprecise to affect the result. There are both practical and theoretical difficulties in determining H. The practical difficulties can be illustrated by the fact that the two most accurate methods, the watt balance and the X-ray crystal density method, do not appear to agree with one another. The most likely reason is that the measurement uncertainty for one of the methods has been estimated too low. It is not as precise as is currently believed. But for the time being there is no indication which method is at fault. The theoretical difficulties arise from the fact that all of the methods except the X-ray crystal density method rely on the theoretical basis of the Josephson effect and the quantum Hall effect. If these theories are slightly inaccurate though there is no evidence at present to suggest they are the methods would not give accurate values for the Planck constant. More importantly, the values of the Planck constant obtained in this way cannot be used as tests of the theories without falling into a circular argument. Fortunately, there are other statistical ways of testing the theories, and the theories have yet to be refuted. Josephson constant. The Josephson constant Kj relates the potential difference U generated by the Josephson effect at a Josephson junction with the frequency I1/2 of the microwave radiation. The theoretical treatment of Josephson effect suggests very strongly that J equals 2Eh. The Josephson constant may be measured by comparing the potential difference generated by an array of Josephson junctions with a potential difference which is known in SI volts. The measurement of the potential difference in SI units is done by allowing an electrostatic force to cancel out a measurable gravitational force. Assuming the validity of the theoretical treatment of the Josephson effect, Kj is related to the Planck constant by watt balance. A watt balance is an instrument for comparing two powers, one of which is measured in SI watts and the other of which is measured in conventional electrical units. From the definition of the conventional watt W90, this gives a measure of the product Kj2OK in SI units, where a K is the von Klitzing constant which appears in the quantum Hall effect. If the theoretical treatments of the Josephson effect and the quantum Hall effect are valid, and in particular assuming that a Ka equals He2, the measurement of Kj2OK is a direct determination of the Planck constant. Magnetic resonance. The gyromagnetic ratio I³ is the constant of proportionality between the frequency I1/2 of nuclear magnetic resonance and the applied magnetic field B, I1/2 equals I³ B. It is difficult to measure gyromagnetic ratios precisely because of the difficulties in precisely measuring B, but the value for protons in water at 25 degrees Celsius is known to better than 1 part per million. The protons are said to be shielded from the applied magnetic field by the electrons in the water molecule, the same effect that gives rise to chemical shift in NMR spectroscopy, and this is indicated by a prime on the symbol for the gyromagnetic ratio, I cubed a euro squared p. The gyromagnetic ratio is related to the shielded proton magnetic moment I1/4 a euro squared p, the spin number I and the reduced Planck constant. The ratio of the shielded proton magnetic moment I1/4 a euro squared p to the electron magnetic moment I1/4 e can be measured separately and to high precision, as the imprecisely known value of the applied magnetic field cancels itself out in taking the ratio. The value of I1/4 e in Ball mountains is also known, it is half the electron G factor Ge. Hence, a further complication is that the measurement of I cubed a euro squared p involves the measurement of an electric current. This is invariably measured in conventional amperes rather than in SI amperes, so a conversion factor is required. The symbol Ia euro squared p90 is used for the measured gyromagnetic ratio using conventional electrical units. In addition, there are two methods of measuring the value, a low field method and a high field method, and the conversion factors are different in the two cases. Only the high field value Ia euro squared p90, high, is of interest in determining the Planck constant. Substitution gives the expression for the Planck constant in terms of Ia euro squared p90, high. Faraday constant. The Faraday constant F is the charge of 1 mole of electrons, equal to the Avogadro constant Na multiplied by the elementary charge E. It can be determined by careful electrolysis experiments, measuring the amount of silver dissolved from an electrode in a given time and for a given electric current. In practice, it is measured in conventional electrical units, and so given the symbol F90. Substituting the definitions of Na and E, and converting from conventional electrical units to SI units, gives the relation to the Planck constant. X-ray crystal density. The X-ray crystal density method is primarily a method for determining the Avogadro constant Na, but as the Avogadro constant is related to the Planck constant, it also determines a value for H. The principle behind the method is to determine Na as the ratio between the volume of the unit cell of a crystal, measured by X-ray crystallography, and the molar volume of the substance. Crystals of silicon are used, as they are available in high quality and purity by the technology developed for the semiconductor industry. The unit cell volume is calculated from the spacing between two crystal planes referred to as D220. The molar volume Vm, C, requires a knowledge of the density of the crystal and the atomic weight of the silicon used. The Planck constant is given by particle accelerator. The experimental measurement of the Planck constant in the Large Hadron Collider laboratory was carried out in 2011. The study, called PCC using a giant particle accelerator, helped to better understand the relationships between the Planck constant and measuring distances in space. Needs citation, fixation. As mentioned above, the numerical value of the Planck constant depends on the system of units used to describe it. Its value in SI units is known to 50 parts per billion, but its value in atomic units is known exactly, because of the way the scale of atomic units is defined. The same is true of conventional electrical units, where the Planck constant is given by with Gja Euro 90 and RKA Euro 90 being exactly defined constants. Atomic units and conventional electrical units are very useful in their respective fields, because the uncertainty in the final result does not depend on an uncertain conversion factor, only on the uncertainty of the measurement itself. There are a number of proposals to redefine certain of the SI base units in terms of fundamental physical constants. This has already been done for the meter, which is defined in terms of a fixed value of the speed of light. The most urgent unit on the list for redefinition is the kilogram, whose value has been fixed for all science by the mass of a small cylinder of platinum iridium alloy kept in a vault just outside Paris. While nobody knows if the mass of the international prototype kilogram has changed since 1889 the value 1 kg of its mass expressed in kilograms is by definition unchanged, and therein lies one of the problems. It is known that over such a time scale the many similar PTA or alloy cylinders kept in national laboratories around the world have changed their relative mass by several tens of parts per million, however carefully they are stored, and the more so the more they have been taken out and used as mass standards. A change of several tens of micrograms in 1 kilogram is equivalent to the current uncertainty in the value of the Planck constant in SI units. The legal process to change the definition of the kilogram is already underway, but had been decided that no final decision would be made before the next meeting of the General Conference on Weights and Measures in 2011. The Planck constant is a leading contender to form the basis of the new definition, although not the only one. Possible new definitions include the mass of a body at rest whose equivalent energy equals the energy of photons whose frequencies sum to 135,639,274 A, 1042 Hz, or simply the kilogram is defined so that the Planck constant equals 6.626068996 A, 1034 A jar S. The BIPM provided draft Resolution A in anticipation of the 24th General Conference on Weights and Measures meeting, detailing the considerations on the possible future revision of the International System of Units, the SI. What balances already measure mass in terms of the Planck constant? At present, standard mass is taken as fixed and the measurement is performed to determine the Planck constant, but, were the Planck constant to be fixed in SI units, the same experiment would be a measurement of the mass. The relative uncertainty in the measurement would remain the same. Mass standards could also be constructed from silicon crystals or by other atom counting methods. Such methods require a knowledge of the Avogadro constant, which fixes the proportionality between atomic mass and macroscopic mass, but, with a defined value of the Planck constant, Na would be known to the same level of uncertainty than current methods of comparing macroscopic mass. See also, new SI definitions, basic concepts of quantum mechanics, Planck units, Stigler's law, wave particle duality, notes. References, Barrow, John D., The Constants of Nature. From Alpha to Omega the numbers that encode the deepest secrets of the universe, Pantheon Books, ISBN A0-375-42221-8. External links, Quantum of Action and Quantum of Spin Numericana, Moriarty, Philip. Eves, Lawrence. Merrifield, Michael. H. Planck's constant. 60 symbols. Brady Heron for the University of Nottingham A.